All right, let's get started. So today we're going to start a discussion of network security, which is going to be a bit of a shift from, so far our discussion has been, what is the bad stuff that happens on a single computer, even if the attacks might be coming over the network. But today we're going to start talking about the network as a network protocol as having security problems of its own. And we have this somewhat weird looking paper that you guys read, commentary by a person that wrote this paper quite a while ago at this point. But sort of the reason we gave you this slightly odd-looking paper is it's one of the few papers that actually talks about the insecurity of the internet. Pretty much everyone since this paper and since those times sort of takes it for granted, doesn't really talk about it explicitly, like, oh yeah, this is how things are broken. But this is one of the few papers that really documents, well, you know, this is what we got wrong, perhaps. So it's interesting to look back and try to understand what are the properties of the internet that we can rely on, or of networks in general. The sort of unique properties of the internet that we worry about in the context of this paper or of security is that it's an open network. And that really makes many of the security problems quite a bit more challenging to deal with. By open network, I mean that we have the internet and pretty much anyone can connect to the internet. There's no need to have a driver's license or any kind of other form of fixed ID or permission to connect to the internet. Anyone can join. And they don't really have an identity up front. This makes many security problems more challenging because you don't know who you're talking to over the internet. Attackers have accounts. They look just like anyone else's account on the internet or ability to connect. So that makes quite a bit of security problems challenging in the internet. The other thing that makes things even more difficult to deal with is the fact that the internet is in many ways quite decentralized. What I mean by the fact that it's decentralized is that even the middle part of this cloud of this internet diagram has many individual ISPs or routers that, of course, connect to each other so that we can communicate, and users probably connect to one of these routers. But there's no one really in charge, or there's not a single entity that controls the internet's operation. And this also makes many security problems quite challenging because, in fact, some of the parts of the internet, like the core ISPs themselves, might be somewhat malicious in some way that we might care about. And defending against that is also a tricky proposition. That make sense? So one thing that's maybe useful to keep in mind is various kinds of security challenges that we might want to deal with in a networked system. And we're not going to necessarily address all of them here, but this is more a sort of discussion of what you might want from a network. One is you may actually want to have authentication maybe or confidentiality for your actual communication of messages you send. This turns out to be something that you probably don't get from the network itself, but is important to worry about for applications. We'll talk on Thursday, next lecture, about how to achieve that for the most part. But there are some things that really are deeply connected to the network protocol itself. For example, any kind of notion of availability or liveness. The fact that you can actually talk to anyone at all. That's also a security property in some sense. Yeah, I'd like to use the internet, and I'd like to use it even if some adversary out there doesn't want me to use the internet. So trying to make sure the internet works despite adversaries trying to take it down, that seems like a security property. And that's really quite core to what the internet is trying to provide to us. And another property that we might care about is privacy. That also turns out to be a challenging thing in some ways to get and depends often on the internal details of the network. That sort of makes sense, hopefully. Any questions so far? All right. So let's look at where these security properties might actually get enforced for us and what happens in the internet for us in terms of security. So many of the host-to-host security problems that you might worry about these days, so this is sort of more of a discussion of where's the internet today in terms of security compared to this paper. A lot of the application-level security problems of host-to-host communication have basically been abstracted away, and they use cryptographic protocols these days. The most commonly deployed protocol is TLS. It encrypts and authenticates communication over the network. And we'll talk about this on Thursday, in Thursday's lecture. So we'll mostly not worry so much about application-level security in this lecture. What we'll really focus on is the core network itself. So the low-level primitives that TLS builds on and that it needs to function. And this part hasn't moved nearly as much as application-level security. So application-level security looks very different from what this paper talks about. The core network looks pretty much the same as what this paper talks about. It's still very much an open protocol, open system. Anyone can join. Many of these issues are still the same. And the one thing that maybe has changed since this paper was written is that I think people have really figured out that the right way to think of these security problems is that we can let applications deal with their problems with encryption and cryptographic techniques like authentication to the extent possible, and we'll really figure out how to provide liveness and maybe some kinds of privacy in the core network. These are the kinds of things that are hard to outsource to the application from the core of the network itself. So in terms of sort of a stack diagram, you probably have applications running on top of some protocol like TLS. TLS runs on top of TCP and IP and maybe UDP somewhere on the side here. So we'll sort of focus on these stacks today, and then these parts we'll talk a little bit more on Thursday and next week. But in addition to this sort of stack view of the world, there's also core protocols that sit on the side, things like DNS that you might need to do name resolution, or protocols like BGP that you use to establish routing information in the network. These are things that are also, well, they're kind of not really underneath TLS in terms of a stack, but TLS depends on them. BGP is needed to figure out where to send packets. DNS is needed by TLS for discovering where to talk to, and also to some degree privacy matters with DNS. So these things are important, and we'll touch on them to some degree today as well. So that's one sort of view of where the internet security has moved on. So in many ways, people have really embraced this end-to-end design where they can use crypto and provide as much security between endpoints as possible. One thing to keep in mind is, maybe more so than any other system we've talked about so far, these core protocols are really slow to evolve. So we looked at web security last week, and that thing was slow to evolve. And that was fast compared to network security standards. These things take a really long time to evolve. And part of the reason is that they're sort of deeply embedded in many systems that are deployed today. They're difficult to change, more so than the web in many ways. So in some sense, we know maybe we could design a better version today, but we're sort of stuck with it for a while. So part of this lecture is sort of a depressing, I don't know, not necessarily depressing, but a factual view of here's where we are today to understand. It's worth knowing, I guess, how the internet works, even if it's, could be done better if we could start from scratch. Sort of make sense? Questions so far? Feel free to ask questions through Richard as well, anonymously. All right. So in light of this, just to sort of maybe underscore what it means to separate the application from the underlying core network in this way, what's the right threat model to have for a network? You've probably seen this already, but it's probably a good idea to spell this out nonetheless. How should you think of the network in terms of security properties from an application's perspective? Well, it's a pretty general purpose threat model. So typically, when you think of building an application that runs over the internet, you probably should think that the adversary can probably observe your data, can observe your packets that you send. And that might be because the adversary maybe controls some routers in the middle that see your data being relayed. Or maybe the adversary controls DNS or can somehow manipulate DNS and get your machine to send data to the wrong IP address, and so on. In addition to observing your data, adversaries can also sort of send arbitrary packets of their choice because they are indeed connected to the network. So we'll see how an adversary being able to send arbitrary packets can lead to some significant security problems for us here. And of course, they can probably modify packets in transit and do sort of almost anything. So one interpretation of this threat model is the whole network is sort of arbitrarily corrupted. It could be looking at your data, sending other data when you ask it to send one thing, etc. And the sort of focus of the network on availability and liveness really means that the only thing going on in the network is they try to make the probability of the adversary dropping your messages as maybe low, but hopefully that's sort of all there is going on. So that's one interpretation of how to think of building secure applications on the internet today is don't really trust the network for much of anything. But it's maybe an overly idealistic view in some sense, because some existing protocols do need to trust the network to some degree. And also, for availability, you do need to get something working. And we'll talk about, I guess, how applications actually try to get their work done despite this threat model. Make some sense? Questions? Hopefully, maybe you already know. If you've done some network stuff, I guess you already have some sense of this. So let's look at one of the attacks. I guess we'll look at various sort of. In the paper talks about a bunch of stuff. Many things are not super relevant from the paper perspective, but a number of things still exist and still important to understand. And one of them that probably good to really understand how it works is this attack that the paper describes with respect to TCP's handshake protocol, how TCP connections get established between two different computers. So the way TCP works is that if you have one computer, let's call it a client, wants to establish a connection to another machine, let's call it S for server, we're actually going to send a couple of messages back and forth in order to establish a TCP connection. And once the connection is established, we can start sending data over it. And TCP tries to provide some properties like they'll actually deliver your data reliably in the face of maybe some network problems like message drops, and hopefully provide some semblance of assurance that a connection really came from this client. We'll see to what extent this is true and to what extent it matters, but here's the underlying protocol. So if you want to connect to some server, what you do is you send it a packet, first of all, and you fill in the whole contents of the packet. So part of the packet is you actually specify the source address. So you say the source is C from a client. The destination is going to be the server. And you put in this field called SYN to synchronize a new connection, and you choose what's called a sequence number. And here, well, you'll choose SNC as your sequence number. So the client picks a random 32-bit integer called SNC to identify its sequence of data bytes being sent to the server, and it'll stick that in the packet it sends. When the server gets a packet like this from C to S with a SYN flag set and a certain sequence number, the server is going to pick its own sequence number. So it'll pick its own sequence number SNS, and it'll, I guess, also remember SNC, and it'll, it has a table. We'll talk about this table in a bit, but it has some kind of a table for connections. It has this connection sort of half open, not quite yet, but it'll be open soon. And the server allocates this SNS number and sends a response back. And this packet says, oh, the source of this guy is S, and it's going to DST the client C. And this packet is talking about a new server sequence number, SNS, with the SYN flag set, and it also acknowledges the client's sequence number. So that's the packet that the server sends back to the client. And at this point, the client can sort of finish the handshake. This is the three-way TCP handshake by sending a packet that says it's from the client to the server, and the packet just acknowledges the sequence number that the server sent back. And at this point, the client can start sending lots of data or whatever request it wants to send, like an HTTP request, for example. And it might actually send some data bytes, add the sequence number of the client, and it'll also acknowledge that the last thing it's heard from the server is this SNS sequence number. That make some sense? Questions about this handshake? How this works? Why this works? Question, yeah. Yeah, so in this case, the sequence number mostly isn't incrementing. I think here you probably incremented +1. So the way to think of it is that the sequence number is almost assigned to every byte being sent on the connection. So here, if I send 10 bytes, I should increment my sequence number by 10. And the only sort of non-byte thing is, I believe, every time you send a SYN, that's effectively like a fake byte. So when you send SYN SNC, you should increment your now counter by 1 more. So now you picked SNC, you stuck it here, and now the next thing you should put as a sequence number of the data you're sending is SNC plus 1 now, because you've sent this SYN. It's not really a byte of payload, but if I remember correctly, the TCP spec says you bump your sequence number after sending a SYN. The same thing with the server here. The next data byte sent from the server is going to be numbered SNS plus 1, and so on. So that's roughly the way these sequence numbers work. And the reason you try to assign a unique number to every byte or event in your flow is so that you can retransmit in case of packet loss. Make sense? Questions about this flow? Yeah. So the question is, does the acknowledgement come with any signature? No, there's no crypto involved here at all. This is just, what it means is that in the packet, there's a couple of fields. Like there's a 32-bit field for the source address and a 16-bit, TCP source port. And there's a 32-bit field in the packet for which sequence number do you want to acknowledge. And you stick it in there, and there's like an extra bit you'd flip to say, yeah, I'm acknowledging it. But yeah, no cryptography involved here. However, there's some sense in which maybe the server really is talking to the client with IP address C. And in particular, whenever data comes to the server, like in this last packet here, the client is sending some data, but the packet must also contain the server's sequence number, SNS over here. And the server is going to check that the sequence number in the packets it receives from the client matches the sequence number it has in its table of active connections. Otherwise, it's not going to be accepted. It's going to be dropped as a sort of malformed or, invalid packet. And in some sense, the sequence number SNS was only sent from the server to the client here to destination C. So modulo, of course, some routers being bad, this packet should only be delivered to the legitimate client C. And as a result, this data must be coming from a machine with that IP address. Otherwise, they wouldn't be able to know what SNS is. Sort of makes sense? At least the sort of intuitive argument for why you might expect to know, why S might expect to have some confidence in the IP address of the machine it's talking to. Make sense? Question?
Is the intention of clients acknowledging the sequence number of the server similar to like a challenge or a non?
So there's a couple of things going on here. So one thing, as a preface to much of this discussion, it's like protocol was designed in the late, sometime in the 70s, I believe, or maybe early 80s. It was quite a long time to get to exactly this protocol. People weren't thinking super clearly about, this is authenticity, this is providing this strict property. But I think it's a little bit of both. So one is trying to provide a challenge response flavor where you can only send this SNS back if you actually heard it from the server. So if you weren't the client, you shouldn't be getting this SNS value, so you wouldn't be able to acknowledge it. The other reason to acknowledge it is so that the server doesn't need to retransmit it. So one problem you might worry about, not a security problem, like this second packet might have been dropped. So if the second packet gets dropped, the server actually is going to wait a little bit, and unless it hears the third packet, it's going to resend the second packet. So then the client, one reason why the client might send this third packet to acknowledge SNS is to tell the server, hey, I got it. You don't need to keep sending it to me. So there's sort of performance and flow control and retransmission logic going on with the sequence numbers. It's actually almost not at all for security, but turns out to have some security implications nonetheless. Question? So if you could redesign this, do you think it's a good idea to have some hash in here? So not super clear. I think many of the problems that you could solve with having a hash can also be solved at the application level by having hashes or maybe even better signatures of application level data. So it's actually not super clear like whether you should put more security properties in this low-level protocol because in some ways, the application really is better suited to do cryptographic key management, for example. like the OS network stack might not really know who you want to talk to, whereas the application might have a sense of, well, which keys are good or not. We'll talk about more about crypto protocols, of course, on Thursday next week as well. Yeah. Okay, so your question is like, if we attack this thing, as I guess we'll talk about in a second, the attack that the paper describes, is that rendered sort of meaningless if you use TLS? Well, maybe yes and no. So we'll talk about this. I guess to quickly answer your question, if you encrypt the payload, you probably wouldn't be able to, and in particular if you authenticate the payload with TLS, you probably can't inject bad commands, but you might be able to terminate connections when they shouldn't be terminated, and that would be a bad thing potentially, depending on the context. Yeah. All right, so let's look at the attack that I think roughly the paper describes on TCP. That sort of surprisingly, you can spoof TCP connections. So here's how that works. So notice that nothing really enforces that the sender of the packet is indeed the correct sender. So we can have a situation like this, where you have an adversary and a server, and maybe a real client somewhere on the right. And the adversary wants to spoof a connection to the server as if it's coming from the client's IP address. And the adversary can sort of mostly do this, right? So all it needs to do is send a packet source from the client, destination to the server, and the sequence number, I guess it's SYN, some SNC. So far, this looks like a totally legit packet that would have been coming from the client, and the source is a field in the packet. It's not a property of where necessarily the packet is coming from. At this point, if the server gets this packet, it's just like that diagram, and the server is going to send a response to C. So it's going to send this packet, source coming from the server, destination going to the client. It's going to SYN a new sequence number SNS, and it's going to acknowledge SN of C. At this point, the client might just ignore this or not. It doesn't really matter too much. But what the server is expecting is that third packet, and maybe the adversary can somehow send that over. So if the adversary sends it, it would look just like this. Right? So destination is to the server. It just needs to acknowledge SN sub S. And then to send data, it looks the same. Now you just send data with the sequence number of the client, and you just have to re-acknowledge the sequence number at the server. So the only thing that's really stopping the adversary from being able to spoof a TCP connection from an arbitrary address is knowing the sequence number SN sub S. And indeed, right, in this attack, the sequence number SN sub S got sent to this client over here. So in order to mount this attack directly or sort of most immediately, you'd have to somehow compromise a router in the network or compromise a routing protocol, which might be a fairly elaborate thing you'd have to pull off. And what the paper describes actually turns out to be, or used to be the case, that it was actually pretty easy to get SN sub S. So before we dive into the details of how we get SN sub S, does this make sense? Does this attack sort of make sense in terms of what happens? And I guess in terms of relevance, how bad is this? Well, it might be bad if you can spoof a connection if you do any kind of IP-level authentication. So the paper talks about these really broken nowadays protocols called RLogin that would let you log into another machine based on the source address from which you're coming. So that seems really bad. And nowadays, no one really uses RLogin. But there's lots of other surprisingly protocols that do IP-level authentication. The sort of most widely used is just SMTP. For sending emails. So if you could spoof address, the reason SMTP uses IP address access control in some sense is to deal with spam. So most mail servers have a database of trustworthy or not trustworthy IP addresses to decide whether some incoming email message should be treated like spam or not. And this heavily depends on the address from which the message is coming from. And if you could spoof connections from an arbitrary address, you would send spam from an IP address of a maybe high reputation MIT server, perhaps, if MIT happened to have a high reputation for SMTP. So that would be bad. That would make many spam measures kind of ineffective. So that turns out to be a big problem. There's other issues as well. So, for example, there's some MIT campus access resources So various things might only be accessible from an MIT IP address, like accessing the library or some databases, journals, whatever. Many things do access control by addresses. Now, these might not be super sensitive, but still kind of annoying if these security measures just didn't work at all. So that's one thing that would be bad if we had TCP spoofing widely available. The other thing, as I mentioned before, is really DOS attacks, where you could reset connections. So if it was possible for me to spoof a connection, I could inject garbage data on a connection, or just close the connection altogether. There's a special flag in TCP I haven't described yet called the reset. So I can include a reset flag in my connection instead of sending data, and I could shoot down an existing connection if I could guess their sequence numbers. So that would also be pretty bad. One way in which adversaries used to exploit this a lot is they would actually reset connections between routers in the internet, and the routers would think, oh, the connection is gone, that means the link went bad. They'd reconfigure the routing for the whole internet. And this caused quite a serious load on the routers just by sending a couple of TCP packets. So these kinds of problems are pretty serious. Also, I guess, yeah, injecting data could lead to sort of connections being closed, maybe a reset, or some other problems arising. So, yeah, pretty undesirable to have TCP spoofing being widely available. But, okay, how do we pull off this attack? What is the paper describing? Question before that.
For things like pretending that you're on a network by having things that are IP level authenticated, could for instance, the MIT campus access, couldn't it be able to tell that the spoofing the TCP because it came in on a external interface rather than internal interface?
So your question is, for MIT's campus access, what's the big deal? Like, why doesn't MIT's router, like, you're MIT, a packet came in from the outside. Well, the answer is things are not as sort of simple as that. Many of the things that are restricted to MIT campus access are actually off campus. Like the journals are not on campus. There's some cloud service, and that cloud service accepts connections and looks at the source, and if the source is an MIT IP address, they might give you access to this journal. Even on MIT's campus, the story is sometimes complicated. It might be that the computer that is implementing this access control policy is not really talking closely to the router. The routers have complicated settings as well. But you're right to think that there's more to the story, of course. And there's some security measures we'll talk about that help. But nonetheless, it seems important to stop TCP spoofing attacks, even though TLS exists on top in some cases. Make sense? Questions? Yeah. So your question is, if indeed SMTP uses IP level authentication, could you spoof Google's IP address and send mail from Gmail? So sort of, yeah, mostly. So you could, if you could actually spoof Google's IP address and establish an SMTP connection as if from Gmail servers, that email message you could claim to be Gmail in the contents of the message, and it would be probably much less likely to be marked as spam if you happen to spoof the IP address. So indeed. Now, we're going to talk about how to defend against this, and it's going to be quite difficult to actually do this in practice, and spammers do other things, but indeed, yeah, this would mean that you could send spam from people's Gmail accounts, and it would appear to be legit. Yeah. Client certificates. Yeah. I guess if we had a different internet and a different way to send email, yeah, maybe it would work, yeah. Indeed. Yeah, question? I'm sorry, how does the attacker get the sequence number? All right, so let's talk about this. So how do we actually choose the sequence number? So what does the server do in order to choose the sequence number? So here's the implementation that pretty much every system had at the time the paper was written. The server just had a UN32 variable called ISN for initial sequence number. And the way this worked is that every second it had a timer that basically incremented the initial sequence number by 128. And every time you have a new connection, what you do is you use SNS as ISN, and then you increment ISN by 64. So this is the rule. This is how you chose ISN, is basically you had this sort of background counter running all the time, this initial sequence number, ISN, and then whenever you needed to use a sequence number for a connection, well, you use that counter, and you move that counter along a little bit faster if you happen to have used a connection. So I guess a couple of questions. One is, okay, so given this scheme, how do you guess the sequence number? Well, now it seems a little bit easier to guess for an adversary. Well, how does the adversary get the server sequence number? Well, the answer is sort of two-step. One is, connect to the server directly from its own IP address. You don't have to spoof anything yet. And this is going to be a real connection. And you're going to get some sequence number, S1. This is going to be the first sequence number. And under the covers, what the server did is it took its ISN variable and it gave you a copy of that variable. That's the sequence number the adversary saw for its first connection. And now the server in the back incremented the sequence number by 64. So now the second step is you spoof and guess that the sequence number for your spoof connection is equal to the sequence number of your first connection plus 64. As long as it didn't take a second for you to do this attack and no other connections came in, this is going to be a pretty accurate guess. Does this make sense? So basically, the server was sharing this initial sequence number variable across all, like for everything going on. And as a result, you could sort of guess what the state of the server was by connecting yourself and then guessing that no other connection came in the meantime. Or if you knew some guess of like how many connections came in, maybe you can have a couple of guesses and you'll be right with some non-trivial probability. So that's the attack that the paper is describing. So this works out, or it used to work out, against most TCP implementations. It was a serious problem. So quick question so far. Does scheme make sense? Yeah, question back there. So you're asking about in this attack, or in the attack on the top board, the adversary sends stuff to the server but doesn't get anything back. Is that what you're pointing out? So what I'm saying is that actually, maybe I should be a little bit more clear. In the first step of the attack, what the adversary does is connect to the server from the source address equals A. It'll connect for real from its own source address. It's a separate TCP connection. It's not spoofed yet. And for this connection, the adversary will get a correct response from the server because, it does have the address. So it will get the sequence number for its legit connection to the server. But the sequence number it gets from the server for its legit connection is related to the sequence number that the server is going to choose for the spoof connection as well, because we know how the server operates in this very predictable way. So that's what's going to allow the adversary to guess the sequence number for the spoof connection based on the sequence number for a first connection that establishes that it isn't spoofed. Make sense? Yeah. Other questions? Yeah. Yes, okay, so your question is, what if the server is under load? So yeah, what you would do is maybe you'd actually measure the load on the server by opening a couple of connections over a couple 100 millisecond period, and you watch what the load is, and then you basically guess roughly what the sequence number is going to be at the point you need to mount your attack. And actually, you can send a couple of packets in your attack. Nothing stops you from sending just one packet, and as long as one of them is right, the server will take your data. So you can sort of play with even a loaded server and get this to sort of work. Yeah. Question? Yeah, indeed. So actually, quite a bit of this, is fine-tuned to worry about overflows and computer reboots. So one reason why there's this weird scheme for initial sequence numbers is that the TCP authors worried a lot about collisions of sequence numbers on short-lived connections that get reestablished. Suppose you open a connection, close it. Open it again, close it again. It has the same source and destination port numbers potentially, and it would be quite damaging if these reopened connections saw a packet from an earlier connection. because it looks legit. And if it happens to have the same sequence number, you could accidentally interpret data from an old connection as really coming in on the new connection. It would sort of cause data corruption or who knows what bad effects. So this is one reason actually why the implementations choose this sort of linearly growing sequence number, because if you were to choose at random, I believe you'd actually have a higher probability of shooting yourself in the foot, because sort of you have a square root of n birthday paradox, where if you have some randomly chosen numbers, the chance of a collision between them is sort of square root of the size, so you'd have 2 to the 16 or 2 to the minus 16 probability of colliding with your own self. But under some assumption about the timing and the rate of connections, this linear growth scheme actually has fewer problems with short-lived connections. So some reasons why they actually carefully manage the evolution of sequence numbers rather than choosing them at random. Now, for a suitably long sequence number, like if it was a cryptographically long thing, like a 128 or a 256-bit sequence number, you could choose them randomly, you'd be in great shape. But I think they were worrying about these kind of connection reuse issues and sequence number collisions, and that's why they had this sort of linearly growing sequence number design. And many TCP implementations actually still really want to preserve this linear growth to indeed avoid these kinds of short-lived connection reuse problems. Make sense to some extent? Questions? All right. So I guess this is the sort of attack. Makes sense how to attack it. So how do you actually deal with this? How do you mitigate these problems? I guess I should say, there's some mitigations around, but, despite all these mitigations, this is still a real issue. Like there was a paper published at a top security conference a couple of years ago that showed how you can still, learn information about connections that you don't really directly see by guessing something about sequence numbers and other properties of TCP packets. This still annoyingly remains an issue just because it's hard to decisively fix this issue in a backwards compatible way. But anyway, so how do we actually try to fix these TCP spoofing attacks? So one is pretty much you want to use probably all of these measures. So one we keep talking about is some kind of application level crypto or TLS. So that'll get you at least to worry about connection resets as opposed to data corruption. So if you encrypt and authenticate your application data being sent over TCP connections, you've probably gotten yourself in a better state, not relying on TCP for data integrity. The other thing that matters a lot for this and other reasons is probably ISP level filtering. What I mean by this is one thing that enabled this attack is that the adversary was able to send packets as if they were coming from the client C, even though C wasn't the adversary's IP address. So this was easy to do in the old internet. These days, many ISPs, like if you have a Comcast cable modem connection at home or something from Verizon, what have you, pretty much every ISP these days will not let you send packets that claim to be from a different source IP address with varying degrees of granularity. Maybe literally your IP address, maybe you can send a packet from an IP address that's outside of your ISP's set of addresses, but some level of ISP level filtering is going to be quite useful to prevent adversaries from sending such packets in the first place. Now, this sort of works for small end users that might have a cable modem connection. For large companies, this kind of filtering doesn't really work out because they may have many connections. It's not clear what addresses are theirs or not, so this doesn't always work. But sort of the most convincing plan is actually, or in addition to all of this, is to actually have a design that's called sort of per host ISN or per connection ISNs. So the idea is that we want to sort of have the best of both worlds. We want sequence numbers or this SNS value to be hard to predict for an adversary, but we still want to preserve this linear growth to deal with short-lived connections. So the idea is to introduce a random offset to the sequence numbers for each connection between every source and destination. So the reason this is going to work is because in TCP, connections are completely disjoint from one another. One TCP connection between one source and destination never really interacts with a TCP connection between any other source and destination pair. So there's no reason to worry about whether sequence numbers between two different connections with two different sources and destinations overlap or not. So what pretty much every TCP stack these days does is actually replace that rule. So the rule I'm talking about is this. So the original TCP design said you should choose SNS to be this initial sequence number that keeps growing. And most modern systems choose the SNS value as that ISN variable that's still basically there, plus a cryptographic hash of some information about the source and the destination of the connection and some per host secret value that the adversary doesn't know. So what this does is it makes sure that in the context of one source and destination for connections that get reused, the ISN sort of grows linearly as before and has whatever collision avoidance properties we sort of talked about. But connections between different sources and destinations are going to have a different hash added to their sequence number. And even if the adversary connects and learns the sequence number for connections between A and S, it really is not related at all to the sequence number that's going to be used for the connection between the C and S source destination pair. So in that case, the adversary isn't going to learn anything useful for spoofing a TCP connection by learning a sequence number for a different source destination pair. Does this make sense? Question back there. So the offset is, or in this design that I've described here, indeed, the offset is deterministic. Like, yeah, this is a, it's like, you can think of it as SHA-1 or SHA-256 in an ideal sense. In practice, this is a 32-bit value, and actually the hash function needs to be faster than this. So Linux uses something not quite cryptographically secure, but doesn't really matter. We're not looking necessarily for cryptographic security. But yeah, it's a deterministic mathematical function. All of its arguments is like source IP, source port, destination IP, destination port, and some secret in the OS. This doesn't really need to be saved to disk. So when a machine boots up, it picks a new secret. But yeah, these offsets are going to be the same. So one thing you're perhaps getting at is that if I can somehow guess what the offset is for one address, maybe now I can spoof connections from that address in the future. Perhaps that's one thing you're maybe getting at. So that might actually be true in the sense that if maybe I can like monitor the network connectivity to your laptop while I'm nearby, near your Wi-Fi, and then when I move away and I don't have Wi-Fi access to your laptop, I still might have some information about this offset, and I could still spoof connections to or from you, depending, yeah. So absolutely, right. So like these defenses aren't perfect. They make some attacks more difficult, like in the context where there's a server far away, you've never talked to it before, etc. But absolutely, this is an offset that's sort of fixed. You could potentially change Linux to maybe like, re-randomize the secret sometimes. But then the question is, how often, what the performance overhead is, how much does this add, etc. So, yeah, this should give you a little bit of a feel of those buffer overflow defenses. We've patched something, it's more difficult to exploit, but if you think carefully, maybe you'll be able to still do some damage here. Yeah. But this is how pretty much every TCP stack works these days. It defeats against at least the simple attacks we've described so far. Make sense? Other questions? Yeah. Well, okay, so your comment is the paper is arguing, well, we shouldn't really trust these sequence numbers, don't trust TCP. So to the extent that this works for you, that's fine. But if we really don't trust it, and if we don't even try to make that fix, it makes it trivial to just, close connections. So if, for example, if I know you're going to go to gmail.com, I can probably guess your IP address somehow. I'll just mount this attack on you against Gmail, and I'll keep resetting your connections to Gmail. I'll prevent you from talking to Gmail. That seems like a really bad thing to do. So in some sense, it's not violating, the TLS guarantees, right? Cryptography still holds. It's not like I can decrypt your Gmail data, but it is sort of attacking the liveness or availability property from the core network. That's the one thing we actually need from the network. We can't get availability just with crypto itself. We need to make sure the network provides some degree of getting data across so we can send at least an encrypted payloads. So you probably shouldn't trust the secrecy of these sequence numbers for like literally the correctness of the email you're going to send, because that probably can be spoofed. But you want some high probability that it's going to work. Otherwise, the whole thing is just going to fall apart. Question back there? Where the secret comes from? Probably from your random number generator, like dev random in Linux when you boot up. That's the servers, yeah. So this is the way the server is going to pick its initial sequence number for a new connection. So there's some secret of the server. This secret is shared for everyone. It gets chosen once and for all. But as long as this is a one-way cryptographic hash function, the adversary can't figure out what the secret was based on the output. Now, it's a little bit funny to talk about cryptographic anything. These are 32-bit integers, but that's the intuition at least. Yeah. Make sense? You got another question? I'm sorry? Yeah, no, yeah, it's like only 32 bits. But again, what we're looking for here is make it pretty difficult for the adversary to corrupt connections, and then we'll get it the rest of the way there with cryptography and TLS on top, once it sort of mostly works. Make sense? So we've talked about sort of source spoofing in the context of TCP. This is mostly a solved problem, as we've talked about. There's various caveats that we've just discussed. One problem where this sort of spoofing shows up again and again, though, is for UDP-based protocols. So UDP just sends sort of one-way messages from some source to the destination address with 16-bit port numbers. They don't really have the benefit of having a round trip to effectively do this challenge response for a sequence number. So UDP-based protocols are much more susceptible to spoofing attacks still. The most prevalent example of that is probably DNS. So DNS spoofing attacks. People realize this is a big problem probably about 10 years ago or so, maybe 15 at this point. And the problem is that DNS runs over UDP, so you just have a client, it sends a query to the server, and all the packet says is, that's a query from the client, the destination is the server, and here's some data. Maybe I'm looking up mit.edu. And that's the query I send to the server, and what I expect back is a response that says, oh, this is a message from the server to the client, and here's the data. MIT.edu's IP address is, 18.70. I don't know. I forget the IP address off the top of my head. But that's roughly how DNS works. And the problem is that there's one reason why the DNS runs over UDP is to have low latency and to provide sort of low overhead resolution. There's no need for having connection establishment. But the downside is that we didn't do a round trip with the server to establish any kind of a secret like SNS. So we just have to, sort of both sides, just take it on faith that the packet had the correct source and destination in it. We'll talk about spoofing client messages in a little bit. That turns out to be a whole other attack. But spoofing server responses is a big deal from the client's perspective. So how do I know? I try to resolve the name MIT.edu. I send a packet out onto some wire or Wi-Fi, and back came this packet. How do I know this is the right response to my query? There's very little sort of secret counters or secret numbers in this request. And indeed, an adversary, right, could probably, if the adversary knows I'm about to go to mit.edu or maybe to gmail.com, the adversary can spoof a response to a DNS query that the adversary thinks I might make. So when I try to go to Gmail or MIT, the adversary is going to also send a packet that looks just the same, claims to be from my DNS server S, but maybe has some other data with the IP address of some IP machine that the adversary controls. So by spoofing DNS replies, an adversary could fool a client into connecting to the wrong server IP address when they go to, for example, some website. Does this attack make sense? And why this is sort of an easier to mount attack because it doesn't actually use TCP? Questions? So how do we deal? What do we do about these attacks? Well, I guess one fix is find more randomness. or find more places to put a nonce. Most DNS client implementations worry these days about this attack, and what they do is they found roughly 30-ish bits of nonce that they can jam somewhere to authenticate the response coming from the DNS server. So the way this works out is that there's a source port number that you can use to send your DNS query. So that's more or less 16 bits of entropy, almost 16 bits. And inside of the DNS query, there's also this field called a query ID. This is an application level field in DNS. Wasn't that important before, but in order to deal with this attack, most DNS clients have repurposed it to store some randomness to make sure the response coming back is legit. And that's another basically 16 bits of entropy or nonce that you can stick in there. So if you want to send a DNS query these days and you want to have some good idea that you're getting the right response back, you should generate a random number and stick half of it in your source port number and half of it in your query ID. And then the attacker's job of spoofing your DNS response becomes more difficult, although not impossible, right? So guessing a 32-bit number isn't that huge of a stretch. So that's one fix for DNS spoofing. Another is to try to do something more principled. Now there's sort of protocols like DNSSEC that actually try to implement cryptographic authentication of DNS records. This hasn't really gotten too much adoption. That's a little bit of a complicated story. Why? Not clear that there's a really single answer. But I think one answer for why DNSSEC didn't really win in terms of deployment and adoption is that it has some pretty non-trivial overheads compared to DNS. DNS is super lightweight. DNSSEC makes many things a little bit more costly, more complicated, etc. And in the sort of time until DNSSEC came about and sort of existed as an option to be deployed, people have figured out how to work around this in many ways. So I think the appeal of deploying DNSSEC didn't seem that great anymore. So some of the things that DNSSEC might solve for us get solved to some extent within TLS, maybe not in a great way, but once TLS exists and many of these other things exist that we'll talk about, deploying DNSSEC doesn't provide that great of an improvement anymore incrementally and comes at some non-trivial costs. I think that's maybe one reason why DNSSEC didn't get deployed. Who knows what happens in the future, but it doesn't seem too great for DNSSEC so far. So I think basically people have figured out how to work around this, and solving it didn't seem like that big of a problem worth paying a big cost for. Make sense? Questions about DNS spoofing kind of issues, etc.? All right. So let's talk about a different class of security problems that are not related to TCP or UDP spoofing directly. And let's talk about DOS attacks. So DOS attacks are really sort of, in some ways, maybe boring attacks. The goal of a DOS attack is to just prevent someone from being able to use a server, just bring it down. But in other ways, it's like the core attack that you need to worry about as an internet designer, because liveness and availability is the only property that you're supposed to provide. So DOS attacks in some ways matter a lot for the internet design in order to provide reachability. So the most sort of interesting DOS attacks we'll talk about is going to be an attack called SYN flooding. And this has to do with overflowing or attacking the server-side state. So we're going to be worrying about this table of connections that the server keeps for TCP connections to it. So the setup is going to be as follows. So typically when you have a server and it receives the first packet of that handshake that we saw over there, let's say from some client, destination is the server, and SYN some SN sub C. At this point, the server needs to remember something in memory about this TCP connection for sort of two reasons. So the server is going to probably have a table that has the source address, the destination address, the SN sub C value, and the SN sub S value. And the reason that the server needs to fill an entry in this table when it gets this connection request is sort of twofold. One is that it's going to send the second packet, and if the second packet gets dropped, well, it should probably resend it, so the client eventually gets it. So that's one reason why you might want to keep an entry in this table. And the other reason is that when the third packet eventually gets back to you, you need to check that the SNS value is actually correct. And the way you did this before is by cross-checking the SNS value from a packet you got with the entry in this table. So this is all going to say that we need the server to keep some entry in this table about these connections that are in the process of being opened. The problem is that we don't know very much about this connection that's being opened yet. In fact, it might be spoofed. We don't know if it's being spoofed or not. I guess if the SNS reply comes back correct, we have some confidence maybe it's not a spoof value. But so far, we've just gotten the first packet. So what an adversary could do is actually send lots of these first packets to the server. So it could send another SYN packet with some SNC, I don't know, prime from a different source. From source, A, source B, source C, all to the server. And for every one of them, the server has to put an entry in this table and send a response back in case this could be a legit connection. And now the server is sort of stuck in this situation where there's sort of two undesirable outcomes. So what are the server's options? One is the server can keep allocating memory and eventually run out of memory. That would be bad, so you could send lots of these packets to the server. It'll eventually run out of memory and presumably crash or reboot or whatever. Or you stop allocating memory, and then you block future connections. So either the server has to stop the growth of this table and say, oh, you can only have 50 or 100 or 1,000 entries in this table, and that's it. Or it can grow forever and run out eventually. So these are sort of both kind of undesirable options. What the paper describes, I think, is that, or what sort of most implementations used to do, is they would just have a limit of about 50 entries in this table for half-open. These are called half-open connections until you got to the third step of the handshake. And once this table is full of these 50 half-open connections, no more connections could be established to the server. So this is a really low-effort DOS attack against the server. You just send 50 packets, and it stops talking. Really easy to attack a server and prevent it from doing anything useful in the future. So this is a big deal. And in fact, it's kind of difficult to defend against these attacks because you don't have a challenge response thing that you've done with the client so far. You don't even know who the client is. Except many things you might try, like maybe only allowing connections from IP addresses you trust, or allowing connections only one per IP address or one per network or anything. All of those are going to break because the adversary can totally fake any source address they want. There's no level of authentication of that source address in order to get into this table. That make sense? That's a really annoying problem to solve. And that sort of, stumped people for quite a while. For, I don't know, I think it was quite a painful, I guess, couple of years on the internet when this attack was discovered by people having to figure out how to fix it yet because it was actually quite easy. Many servers were being attacked. So if that attack makes sense, let's talk a little bit about how we actually go about solving this. So in order to make these SYN flatting attacks less damaging, what you basically have to do is figure out a way to reconcile these two requirements. One is you don't want to allocate state on the server before you've authenticated the client, because that leads to DOS attacks where you're allocating memory, but the client hasn't really ponied up any resources that are expensive to the client. But the requirement is that even though we don't want to be allocating memory, we still need to be able to authenticate this SNS value that comes in that third packet. So how do we authenticate that SNS value without storing state? Well, sort of use a little bit of crypto, very much like that solution to the ISN problem. This technique is called SYN cookies. And the design looks roughly as follows. So, or the goal, I guess, as I was describing, is to make sure that we can still authenticate SN sub S without storing any server-side state. So the way SYN cookies work is that we're going to choose SN sub S in yet another way. That's going to be sort of an alternative to the formula we have over there on the right. And a server could sort of choose to go into the SYN cookie mode if it thinks it's under attack. Like if the table starts growing and it gets to a large number of entries, we can switch the way we allocate these SNS values and maybe defend ourselves against the SYN flooding attack. So the way we're going to choose SNS values in the SYN cookie design is we're going to actually sort of rely on the client value and some offset. So we're going to take the client's sequence number from the packet and then add to it this value, which is sort of two things bit concatenated together. So one is a coarse grained timestamp, roughly, what time it is right now. This is going to be a very coarse grained thing. This is like, minute granularity. So it doesn't step too quickly. It doesn't actually need to be too fine grained. Concatenated with sort of a short cryptographic-ish hash. I mean, it's less than 32 bits at this point. Not super cryptographic, but it's going to be a hash of the source and the destination, very much like we hashed before, and this timestamp, and another kind of a secret value. So why is this construction going to be helpful for solving the SYN flooding problem? Well, one thing is this lets us compute an SNS value based on the SNC value in the first packet of the TCP handshake. So we compute this SNS value, and we send off the second packet. And then we forget about the connection at all. We don't need to keep any server-side state. So now there isn't really a DOS attack going on. But the cool thing is that if a third packet ever does come back, maybe it's from a legit client, we can check if that SNS value is what it should have been sending us by taking the SNC value from the client's third packet, because it has to, I guess, not sort of shown here, but really even this packet would have had sort of no data and SN sub C included in it. I didn't really write it down because it didn't matter, but every TCP packet has the client SNC value, and then from that we can subtract it away, get the timestamp, compute this hash, and see if the hash we recompute based on the source destination timestamp with our secret matches what is actually in the SNS value the remote machine sent us in step 3. This is kind of a clever design that allows us to check the correctness of this SNS value without storing any state. You can think of it as a very cheap form of a cryptographic hash, limited by the fact that we only have like 32 bits of space to play with and has to be backwards compatible in some way. This is why we added to SN sub C so that it grows linearly as long as the client grows their sequence numbers linearly. It's kind of a cute design. But this is a nice scheme that pretty much every serious server TCP stack implements these days and defends against these SYN flooding attacks. So even if a server gets a lot of these SYN requests, it can switch into this mode, send these stateless SNS values back, and avoid those sort of two bad outcomes. Make sense? Question?
So you can lift part of the memory requirement for the connection by using SYN cookies, but then for every incoming connection, you need to compute a hash or whatever. So it sort of lifts
So your point is, okay, so we stopped allocating memory, but now we're still doing some computation. So indeed, so this hash is actually like a pretty cheap hash. This is not a SHA-1 or anything. It's actually a pretty cheap hash. I forget what actually gets used in Linux these days. It's like some SIP hash or something really lightweight. Sort of slightly hard to reverse, I suppose. You want that. You don't want to get the secret out. But at some level, you're right that we've traded a little bit of memory use for a little bit of computation. The cost of computing this sequence number is probably fairly small compared to the total cost of handling a packet at all. And that's why probably this is a reasonable trade-off. Especially memory lasts for a very long time. This stuff you can get, more cycles every nanosecond. So it's a more renewable resource in some sense. But it's a good point. We need to worry also about sort of server-side CPU use and bandwidth use and all these other resources for all of them could be potentially targets of DOS attacks. Make sense? Other questions about SYN flooding, SYN cookies? All right. So another kind of DOS attack I wanted to describe is sort of maybe a more mundane form of attack, if you will, sort of bandwidth flooding. So instead of trying to exhaust the server's memory, which is kind of clever and interesting looking. You could sort of have maybe a more brute force attack where you just send lots of data to a server, and if you can send more data than the server has bandwidth for, then you might actually overwhelm the server, and it'll have a hard time keeping up with legitimate requests. So that's a kind of a boring form of DOS attack in some sense, right? Like bandwidth attacks. But there are some clever variants of bandwidth attacks that are called bandwidth amplification attacks. So the idea with bandwidth amplification is that, okay, so I guess the thing I was talking about before is you just have a client sending lots of packets to the server, then, the picture looks pretty symmetric. If I have more bandwidth than the server, that's great, I can overwhelm it, but if the server has more bandwidth, well, it doesn't really do much to the server. The cleverness of bandwidth amplification attacks is that an adversary might be able to trick other machines into sending data to the server. And this in particular is going to work well with UDP-based protocols that don't really authenticate the source of a IP packet very much. So one example, I guess not even UDP, but ping-based attacks, these were sort of maybe the first bandwidth amplification attacks people discovered, is that over IP, there's a protocol called ICMP that, among other things, you could use to ping a remote machine. So you send it a ping packet, and it sends you a ping packet back, a response packet back, so you can sort of measure some latency or whatever. One thing that was sort of a surprising feature in retrospect is that in IP, there was a broadcast address of a network that caused the packet to be delivered to every machine on a particular local network. And this worked even for ping packets. So what an adversary might do is that maybe at MIT there's a local network that has a bunch of machines connected to it, like in, I don't know, one of the buildings, like in building 26 here, could be all the wireless laptops or all the machines plugged into Ethernet in building 26, could be a network at MIT, and an adversary could send a ping packet to the broadcast address of MIT's building 26 network. So destination of the packet might be 18. I guess I don't remember offhand the IP address of building 26, but 26.7.255, that's the broadcast address of our research network, for example. So if an adversary sent a packet there, every machine on our research network would get this packet, and it would respond. Well, where would it respond with the response to this ping packet? Well, it's whatever in the source of this packet. So if an adversary put the source as the address of the victim, then every machine on the subnet would send a reply to our victim. And if there's many machines on the subnet, every one of them is going to send this reply. So if an adversary sends one packet and there's 100 machines here, the victim gets 100 packets now. So this is a big amplification factor for the adversary, and they can, probably even with relatively modest bandwidth on the attacker side, they can overwhelm a victim server now. So this is a situation where you don't sort of bad for a victim, good for the adversary. They can use potentially lots of networks, not just MIT's network, but any network that has these broadcast addresses enabled. This is going to be bad for victims. This sort of style of attack makes sense? So this particular attack doesn't really work anymore. The way this got fixed is pretty much all the routers had to be reconfigured and updated in their software to not send ping packets to broadcast addresses. This was sort of a fairly manual and high-effort fix on pretty much every router deployed on the internet. But that sort of had to be done in order to stop these attacks. The problem is that sort of these ping packets aren't the only thing that work this way. A pretty common amplification attack that gets used today, sort of right now, to this day, is DNS-based amplification. And the reason that DNS amplification works is that DNS looks just like this ping protocol in a sense, where it doesn't really authenticate the source of a query. So if a client sends a request to a DNS server, it can specify whatever source it wants. And the sort of interesting property of DNS is that the data, the query might be actually a small packet. It might just say, I just want to look up MIT.edu. But there may be many records for MIT.edu that the server sends back. So even though it doesn't look like sending a lot of packets to a victim, the response is much bigger than the query here. So you might send a 16-byte query, and the response could be, I don't know, almost a kilobyte or 512 bytes at least. So that's a big amplification factor as well in terms of bandwidth, even if it's not amplifying the number of packets. So the way DNS amplification would work is the adversary would send a packet to the DNS server where the source is the victim and some short query, and the DNS server is going to send a reply over to the victim machine, and the replies could be much larger in terms of the bandwidth packet size than the query. Again, given the adversary a pretty serious amplification factor. Make sense? These kinds of things are actually quite difficult to solve. I don't think anyone's really figured out a great plan for what to do with DNS amplification, partly because it's like sort of by design. It's hard to really do much to prevent this attack in the first place without breaking the way DNS works. So people mostly just live with this sort of a fact of life on the internet, unfortunately. Question? Okay, so ISPs. Okay, so this I guess we talked about like point 2 over here. ISP level filtering helps somewhat. So in order to do this DNS amplification attack, you basically have to run this DNS amplification attack from a point in the network that doesn't apply that kind of source level filtering to you, and that might be either a not very well run ISP. So okay, you just have to find sort of the worst ISP out there, and it'll work fine. Like you might not subscribe to them, but the adversary will happily subscribe to them. Or you find a large company for which the ISP doesn't apply source level filtering. So for example, MIT has a fairly complex network and a complex relationship with its ISPs. It has multiple ISPs, and my understanding is I don't think MIT's ISPs apply source level filtering, or at least not particularly strict source level filtering to MIT's traffic. So if someone compromised a machine at MIT where MIT's routers didn't filter that machine's source level traffic, well, MIT's ISPs might not either at that point. And okay, so I guess this is the example where security really is a function of what's the worst configured router out there, not the best or average. But you do have to do a little bit of work. Like you probably wouldn't be able to do this directly from your Comcast connection. Other questions? All right. So let's talk a little bit about other sort of families of security problems on the internet. So we've talked about, I guess, TCP spoofing and source spoofing attacks, DOS attacks. Let's talk a little bit about routing attacks. So routing protocols was another thing that the paper touched on a bit, and sort of still remains a big problem on the internet today. Hasn't really been solved that much. So in terms of routing protocols, it's really sort of two levels of routing protocols that you might think about. One is really local routing protocols where you might just worry about, okay, so here's your MIT network that you connect to, and you might plug into your MIT network in your dorm room or connect to it over Wi-Fi, and somewhere on that network is the MIT router that's going to connect to the rest of the internet. So you need routing protocols at the level of this local network as well to plug in the first place and connect to the router, and then the router needs to have some routing protocol to talk to the global internet. Both are not particularly well secured. So on the local side of things, the way that things work is pretty much everything is just broadcast. There's absolutely no security at all. So when you connect to Wi-Fi or you plug into your Ethernet port in your dorm room, you speak a protocol called DHCP, and that thing just broadcasts out there. So when you connect, it broadcasts a message saying, I want an IP address and I want to know what the DNS servers are. And some DHCP server responds and says, here you go. Here's an IP address. So the response is going to set the IP address of your computer. It's actually going to set the DNS servers that you use, and so on. And all of this is not authenticated in any way. You just send out a request saying, I want an IP address. Anyone that wants can send a response to you. Here's an IP address. Here's some DNS servers you should use. And in some sense, it's unavoidable because when you just plug into a network or connect to it, you have no a priori knowledge. What is the right router you should be expecting a message from? So in some ways, this is sort of an unavoidable property of being able to connect to an open network or largely open because it's not actually clear who should you expect a response from. And similarly, once you're already connected, if you want to talk to some other machine on the network, like you want to talk to another computer or you want to talk to the router, the way you figure out how to send them packets is use a protocol called ARP, Address Resolution Protocol. It's also a broadcast protocol and kind of a simplistic thing. You just say, I'd like to send a packet to the router. Who wants it? And anyone can respond. Similarly, there's no real authentication of this protocol. So very much like a local network is just broadcast. There's very little security or authentication of any kind going on. To some extent, sort of, I think, as I was arguing, I think somewhat inevitable. But at the global scale, things also look fairly weak, if you will. So, as we talked about, I guess on the large scale between routers that comprise the internet, there's some global routing protocol going on. And these days, it's BGP, pretty much universally. The paper talks about some other protocols like RIP, etc. Those things aren't really that widely used and don't really matter quite as much, but BGP is absolutely the main protocol used. So when we sort of draw this picture, or I guess I erased it, but the internet has a bunch of routers. Well, they all talk this protocol called BGP to each other, and that's how they decide which routers can send which message, or which routers should receive packets for which IP address. So the way BGP works is that there are some participants in this BGP protocol. These are probably ISPs or backbone providers, large companies, organizations like MIT. They have routers that participate in BGP, and they connect to each other and talk to each other roughly along lines of physical connections between them. So if MIT has a link to some provider like Cogent, well, not only is there a fiber link, there's also a BGP connection between the two routers on both sides. And the protocol that they speak is actually fairly simplistic. So basically, any participant can announce an IP address. And I guess they typically don't announce one address. You announce what's called a prefix, so like 18.26.***, which you would write as like /16. But you would send an announcement from one router saying, please send all the packets for this destination to me. And every other participant in the BGP just relays this announcement to other participants saying, I know how to get to this. This router told me. They'll take those packets. And the BGP protocol is fairly open in terms of who can send these announcements to each other. There's very much like in TCP spoofing we were talking about, there's some ISP level filtering for really small participants in BGP. Other participants apply filters and say, you can only send these announcements. I know, you only have one IP address, that's it. It's the only prefix you'll ever send. But for serious participants that have many connections, there's very little filtering being applied to them, and they can announce basically any address they want. And that's how it works. So it's very much this sort of open routing protocol the paper talks about. And there's been some attacks. I'm not going to repeat them again here. I think we talked about them in the first lecture. But it's quite easy for some adversary to announce a prefix of YouTube or Gmail or any other provider they care to intercept packets for example. Slightly unfortunate situation in some ways. There's some fixes. There's many protocols that people have designed that might solve this. There's a protocol called SBGP. There's a protocol called RPKI. There's a more serious protocol called BGPsec. A couple of other options. They're slowly being deployed. In particular, the thing being deployed is this thing RPKI. It's kind of an intermediate level of security, if you will. It basically signs announcements. So when you want to announce a prefix, you have to sign it with a cryptographic key. And there's going to be some maybe centralized database of who's allowed to announce what prefix. Sort of helps in some ways, but doesn't fully solve the problem. You can, someone announces this prefix, but you can take their announcement and you can inject it from another side of the network maybe. And depending on exactly the settings of how RPKI is configured, that might actually work. So the details, I guess, matter in terms of which attacks can still be pulled off or not. But I think the high bet is, in many ways, the global routing protocol is also still quite vulnerable to adversarial participants. And again, I guess the reason this works out is that, for the most part, people monitor this manually, and if there's bad announcements, they manually disconnect participants that seem to be injecting bad prefixes into the network. And and the rest sort of gets handled with crypto at the application level. So again, this is a case where if the internet mostly works, that's okay. And TLS takes care of the rest at the application level. But it is kind of unfortunate that still we don't really have strong guarantees about routing security. And this also translates into some privacy concerns as well. So some adversary might be able to announce your IP address prefix and monitor who is talking to you, even if for a little bit of time, even if they can decrypt the messages. All right, so that's sort of the state of network security, minus all the crypto and application level security. We'll talk about that on Thursday. See you guys then.
Two. So I'm kind of blocking it here. What do you think? All right, good. And power. I'm assuming you want power? Okay, so that's. I've just run one single cord. So let's get. Do you need an adapter? I have it if you need it. And then for the NHDY. Oh, I got that adapter too. Okay, all right, I've got it. Okay, so this power.